You see how when I'm typing with R, I'll go question mark rbinom here. So the question mark gives you help, and we covered this yesterday. And rbinom will give us random numbers from the binomial distribution. And we were covering this yesterday. So let's just have a look at that. And we've got a whole bunch of help. There it all is. And we talked about some of this yesterday. See how the formula here, see how that formula I'm highlighting there, see how this formula here matches the one which I've just written down there. So we're on the same page and we know what we're doing. Okay? So let's just play with that. Let's just have a look at that for a moment. Let's try, let's go back to rbinom. If I go args of rbinom, it's like a poor man's help. So args of this function here, n, size, and prob. There's a little bit of a confusion here because n is the number of observations to take, and what they've called size is what I've called n. And we'll see how that works in a minute. Because if I go rbinom, let's say 10, 5, 0.5, what we see here is we're going to have 10 observations, size 5, probability of success 0.5, and indeed we did this yesterday. So we've got 2, 2, 2, 3, 2. Sometimes you have 2 successes, sometimes 3, sometimes 1, sometimes 3, 2, 3, 3, 2, and so forth. Okay. So we can play with this. If I do this again, of course it comes out different because it's random numbers each time. And of course I can change the probabilities, 0.9. What I want to get across to you is the fact that I'm mucking around with this formula here, but what I want to do is to encourage you to change the values of these parameters just to make sure that you understand what's going on. Okay? So let's have a look at that. And I think we understand what's going on there. I've also got the dbinom function. Now the dbinom function, instead of rbinom, we've got dbinom here. What that does is calculate this for us. Okay? So what I'm going to do is just to verify that we've got the correct answer. And I'm going to use, as an example, I'm going to use n equals 5, r equals 2, and p equals 0.5. And I'm going to evaluate that in 2 different ways. And I want to encourage you, this is kind of a keynote concept in this whole course. What you have to do is verify your thinking by getting the same answer 4 or 5 different ways, as many ways as you can think of. If you've only got 2, that's good. If you've only got 1, well, that's all you've got. But if you can think of another way to evaluate a probability or to evaluate a sum, then always do it in as many ways as you can, just to verify your thinking. In my research, when I come across a function or an expression which I want to evaluate, if I can think of another way to evaluate it, I've got to do it, even if I've done it 5 different ways. If I think of a 6th way to do that, I won't stop until I've done it that 6th way, just to check that I can, even if the 6th way is very, very complicated. So I joke with my children about this. I say, well, a nice trick for adding 1 to a number is add 17 and then subtract 16. Yeah? It's like a joke, but it should work, and it had better work. And if you can think of a complicated way to evaluate something, it had better work out to be the same answer, or something's wrong with your thinking. So I'm going to evaluate this. I'm going to evaluate this probability here, or the probability of this. Let me write it out a bit more explicitly. Probability that r equals 2 when n equals 5 and p equals 0.5. And I'm going to evaluate it in 3 different ways. The first way is just to do it directly. Let's do it here. Let's just write out that formula. Oh, I've scribbled it off now, haven't I? So it's n factorial over r factorial n minus r factorial. Okay? You should be able to write that without thinking. There should be no thought at all. You should just be able to write it down. N equals 5, r equals 2, p equals 0.5. So it's equal to 5 factorial over 2 factorial, 3 factorial, times 0.5 to the power 2 times 1 minus 0.5 to the power 3. See what I'm gaining by writing out the formula. I'm just making sure that I understand all the terms in this equation here. I've got all the information here. All I've done is write the formula out again, and I've just bunged the values in here. So 5 factorial is 1, 2, 3, 4, 5, over 1 times 2 times 1 times 2 times 3. You're all familiar with the factorial function? Yeah. Times 0.5 squared times 0.5 cubed. Now what I was going to say, and I've broken my own rule, is just do one thing at a time. And here I've done 2. See, I've expanded the 5 factorial to 1, 2, 3, 4, 5. And I've also done the 1 minus 0.5 to 0.5. So I've done 2 things in one line. And I don't like that. Normally I just do one thing on a line, because it doesn't hurt. Just go through it slowly. I mean, it's nice to be clever and do 5 things simultaneously, but if you can't, there's no problem. Let's go to the top of the board again. Let's do some cancelling here. I can cancel those 2's, I can cancel that 3, and I can cancel that with that one to make 2. So I've got 2 times 5, which is 10, times 0.5 to the power 5. Are you happy with 0.5 squared times 0.5 cubed being 0.5 to the power 5? Yes? If you're not, stop me. All right? Which equals 10 over 2 to the power 5. You happy? You happy with that to that?
Sure.
Yeah? You happy with 0.5 being a half?
Sure.
Yeah? Stop me if you're not. 10 over 32, which equals 5 over 16. And that's my answer. So what we've done is evaluate the binomial distribution for n equals 5, r equals 2, and p equals 0.5, coming out to be that. Now, at this point, I reveal that there's a shortcut. I can go dbinom. Actually, I'll go args. Oops. Args of dbinom, which gives me x, size, and prob. And we know that the size is 5 because we've got 5 observations. X is going to be 2. What he's called x, I call r. And the prob is 0.5. So we just bung it in and see what happens. dbinom of x size prob 2, 5, 0.5 comes out to be that. And of course, that matches my answer of 5/16. And for those of you that can't divide by 16 in your head, we'll just do it cheating. And you see we get the same answer. So it's checking out in this very, very basic sense. If I go rbinom, let's say 35, 0.5. Just a minute, let me make this a bit bigger here. I'll do that again with a few more trials. What we see here is random numbers from the binomial distribution, size 5, probability 0.5, but I've got 300 repeated trials here. So that's number 298, that's trial 299, and that's trial 300. So this is like having a hospital with 5 patients in. Probability of curing or failing to cure is 0.5. And we write down how many live and how many die. And sometimes we have the zeros. Is there a 5 in there anyway? Oh, there it is, 5. So what I want to do is to use and this is another keynote concept in the whole course. I want to use numerical simulation to demonstrate this 5/16 is correct, this 0.3125 is correct. So what I'm saying here, this number here says, here's a problem because I'm pointing to the screen and they'll only get, we'll sort that out. What I can see here is that about 31% of my trials will have exactly 2 successes in. So out of these numbers here, we're going to expect about 31% of my 300 to have a success of 2. So what I'm going to do is make a table. Actually, I'll do it 1,000 because it'll be easier. There's 1,000. There you go. So it went right, it scrolled up off the top of the screen, 989 up to number 1,000. And what I'm going to do is to make a table of those. Now, what do we expect to see? What we expect to see is 31% of these trials to have exactly 2. And there's some 2s in here, there's some there, some there, some here, some there. 31% of 1,000 is 312.5. So we'd expect to see close to 312.5 trials. And look, we see 315 here. So we expect to see what was it? It was 1,000 times 0.3125, wasn't it, yeah? So we'd expect to see 312.5, and we see 315, so it's very, very close. So what we've got is not quite a proof, but a verification that our thinking is correct on this binomial distribution. And I've come at it in 3 separate ways. Once with dbinom, once with working it out directly from the formula, and once by numerical verification. Okay. I'm now going to introduce, using the binomial distribution, I'm going to introduce the notion of hypothesis testing. So let's just say that we've got a sequence of 10 soccer matches. And let's just say that we have 8 home wins and 2 away wins. And I'll stop in about 5 or 10 minutes. I'll have a break. Those of you who play soccer will know that the home team's always got an advantage because you're playing with your own crowd there and you know the pitch and everything just works for you. And when the visitors come, you give them they are at a disadvantage because they're playing away. They've had to travel and there's a whole bunch of other reasons. So let's just say that you're investigating this. You're investigating home team advantage. Okay, and you get some data. This is your data here. You have 10 matches that you've looked at and you've chosen. Of course, if you're doing this professionally, you can have a lot more data, but this is just a nice simple example. And what you do is you hypothesize that the home team is at an advantage, because of all the reasons I've just mentioned. Because the away teams had to travel, because the home teams got their a larger support, maybe that'll buoy them up, and so forth and so forth and so forth. This is extraordinarily difficult to think about. It's not just a matter of scientific measurement here, because we've got uncertainty in here. Because everybody knows that soccer, well, any game has got, I'm ignoring draws here. Ignoring draws. Any sport has got random events in it and random component to it. And so we can't actually prove anything for sure, for definite, using the methods of statistics. But what we do, or what we can do, is say, well, hang on a minute, we have got more home wins than half. There's more than you'd expect 50-50 if it's an exactly even game. So if the home advantage does not exist, then P equals 0.5, equals the probability of a home win. And you say, but the home advantage does exist. But the way to investigate it is to hypothesize that it doesn't. This is called a null hypothesis. And as I was chatting to a few of you yesterday, we're going to need some revision on this. So we set out a null hypothesis that there is no such thing as home advantage, or that home advantage doesn't exist. So you normally write it down H0, that's your null hypothesis, which says that the probability of a home win equals 0.5 exactly. H0 is just a mathematical way of saying home advantage equals 0. Because it's 50-50. If this is true, you really have got a 50-50 probability of home winning. Because, yeah. Now, it's one thing to say that we've got more home wins than you'd expect. Well, you'd expect 5. Because it's 50-50 out of 10, you'd expect 5, right? But we've got 8 here. But it's quite consistent. This observation here is quite consistent with this. If I ran Bernoulli simulations, I'll show you. Let's try it. Let's try it. Let's have a whole bunch of... If I make that 10 instead, yeah? This is how many home wins you get. Did you see this? I'll just do it a few smaller so it doesn't go off the screen. There you go. From time to time, this is when the null hypothesis is true, because I've forced it to be true here. All right? From time to time, you get 8. Sometimes you get 10. If that happened, everyone here would say, look, we've got 10 out of 10 home wins. That means there must be a home advantage. But no, there isn't. Because here, I've forced the null hypothesis to be true, the negation of what I'm investigating. I'm investigating the home advantage. The null hypothesis is it doesn't exist. Why do I do that? Fundamentally, I do it because it's easy to work out the consequences of the null hypothesis. The null hypothesis is easy. It's like tossing a coin. There'll be other examples we'll see later that are a little bit harder, but fundamentally, your null hypothesis, the reason you go through all this, the probability of this, and null hypothesis that, the reason you go through it is that you can see what the world looks like if the null hypothesis is true, because I can just whack it in there. And sometimes you get extreme answers like this. There's a 0 there. Well spotted. Is that the only one? Okay.
So you can lose them all or win them all.
You can lose them all or win them all. But you say it's not very likely that you'll win all 10. Yeah? If the null is true, and that gives you some evidence. We'll cover this a bit more formally later on, but that gives you, if you did see 10, or for that matter 8, it gives you evidence that the null is false. You need another piece in the jigsaw here. HA equals the alternative hypothesis equals that P is greater than 0.5 equals home okay? Null hypothesis, no home advantage. Alternative hypothesis is that P is greater, strictly greater. Notice I'm writing greater, not greater than or equal to. All right? And so what we ask is this. We ask, how likely is it? Oh, it's there. The question we ask is, let me ask you, well, I'll put some ones that aren't quite right. We ask, if the null hypothesis is true, how probable is it that we observe the data? Which in this case is 8, 2. And for reasons that will become clear when we talk about continuous distributions, well, for reasons that should be obvious right now, we actually ask, if the null hypothesis is true, what is the probability of observing our data or an observation more extreme? Which you will have seen last time. The reason we do that is that if we've got our data set of 8, 2, our data set of 8 home wins and 2 away wins, we really ought to count 9, 1, and indeed 10, 0, as somebody mentioned. Those data sets here are just as surprising, in fact, more so than seeing what we're seeing. We actually observe this. This is our observation here. But these data sets here, it could have been 9, 1 or 10, 0. Those should be part of our thinking. We really ought to be including those possibilities in our thought processes. If the null hypothesis is true, what is the probability of observing our data or an observation more extreme? Which in this case is observing 8, 2, or 9, 1, or 10, 0. And this is why it works. I can answer that question. It's perhaps not the question you want to answer. It's not really what you're interested in. What you're really interested in is, does the home advantage exist? That's what you came to me asking. And I'm answering a different question. But I can answer this, and I can't ask the question you want to answer. And that's a good start. It's not perfect, and indeed it's an ongoing matter of some quite acrimonious statistical debate as to whether or not this approach in fact is even meaningful. But it says learn p-values in your learning objectives, so that's what you're going to get. Okay, well I can answer that question using the binomial distribution. The null hypothesis clearly states that p equals 0.5, so I seek the probability that r equals 8 or 9 or 10, which is the number of home wins, when n equals 10 and p equals, oh, I've got it there, 0.5. So I can just figure that out using dbinom. That's the probability of getting 8 victories, 8 home wins out of 10 trials, probability 0.5. That's the probability of getting 9 victories out of 10. See how the probability is even smaller? And there's one more, of course, 10. I can stop there because there's no way you can get more than 10 out of 10. Yeah? So 8, 9, and 10. And here, what is the probability of observing our data or an observation more extreme? Well, it's the sum of these probabilities here, because we've got 0.04, 0.0097, or 0.00097, and we've got to add them together. So I'll do that for you. I'll do it in several different ways. I'll do it in 3 or 4 different ways. What time is it? And then I'll stop. 8 plus dbinom 9 out of 10, 0.5, plus dbinom 10, 10, 0.5. Okay, and there's our answer. That plus that plus that, see I've just written it out like that. I can do it a little bit more neatly if I want. I can do it a little bit more slickly. I can do that and do them all in one go. Remember the colon operator takes you 8, 9, 10, and so that is this, that is that, and that figure there is this one here. And of course what I want to do is to take the sum. The answer for this is 5.46% answer. So the way to think about that is that if the null hypothesis is true, we observe r equals 8 or 9 or 10 about 5.5% of the time. And we refer to that 5.5% as a p-value. And I've got to stop now because it's 10 o'clock and we need a break. The answer to this question is defined as a p-value. And I will come back again and again and again to this method of inference. Okay, and we've calculated what the p-value is. It's 5.5%, and I will interpret it in the second half. Right, I'm going to stop there.